what I see now is two geological profiles, and between these two profiles I have the fault plane. Okay, this is one profile, and the layers are my fingers. And this is the other profile. And what the fault does, it changes the way that these layers are put against each other. And this is called a fault plane diagram. These are very famous structures in oil geology, and everybody who works in oil exploration or production will learn how to use these and how to make these diagrams. So, what I see now is here is my layer, and this is the fault tip, and one side goes up and the other side goes down. So I've just shown you this bit here. But if I have 1, 2, 3, 4, 5, 6 layers in the same sequence, then what you see is that all these layers become connected. Because of this juxtaposition, fluids which are, for example, in this brown layer, dark brown layer, can now flow into all these other layers. So, very simply, small faults in a sequence of reservoirs and seals, like sands and clays, they get completely connected by faults which juxtapose the layers against each other. And if you don't know this juxtaposition, if you don't understand this juxtaposition, you cannot study fault seals. It's an essential part of that. In very simple diagrams, like the one that I've shown you here, it all looks very schematic. But if you make real fault plane diagrams of a real fault, then you will see pictures like this. And I don't have a lot of time to explain this to you, but it will come back in next year's advanced structural geology course. What you see here is a fault, and on one side the layers go like this, and the other side the layers go like that. And fault plane diagrams explain to you how these layers are juxtaposed. Okay? So that's very important. The other important thing that you have to understand about the fault plane is the permeability of the fault plane itself. In this diagram here, the fault plane is very open. It has got big fractures. But other fault planes can be full of clay and be completely sealed. So what do we have to think about these fault planes? Well, here are a few examples. These are photographs which I took of faults in sand-clay sequences. So the clay is impermeable and the sand is quite permeable. And here you see a clay layer going into the fault, going up and coming out again. Here is a much bigger fault plane. This could have 100 meters offset, and the whole fault zone is maybe a meter wide, and it contains of completely sheared and reworked clay with big lenses or fishes of sand floating in it. And you can imagine that if you have a lot of clay in the fault zone, it will basically become impermeable, because clay is a very good seal. One of the classic areas of clay in faults are in fact in the brown coal quarries here in North Rhine-Westphalia, in Hambach or other quarries. And here is a very beautiful picture that I've taken in one of these quarries. This here is a clay layer which is moved down, and here the scientists in the mine have excavated this clay layer at the floor of the mine, which is inside this fault plane. Okay? And the reason they studied this is because they had a water breakthrough. So they were mining, and one day, quite unexpectedly, water started shooting out of the ground. It was in the newspaper because, of course, it threatens the safety of these mines. And to understand these kind of water leakages in the brown coal mines, you have to understand the property of the fault plane and also the juxtaposition. So, how does this fault plane look like? And I went to have a closer look, and I saw this picture. Okay, Okay, so this is a coin. This is just 25 centimeters. On the left side, it's white sand. It's one of the sand layers. On the right side, it is brown coal. It's lignite. And this fault has moved about 70 meters, so about 5 times the height of this building. And between the two blocks, I formed a fault gouge, which is basically a mixture of the white sand and the brown coal. You can already see it. It is about the color in between the dark and the white one. And it is, you could do the same by mixing it in a mixer. But what is interesting is that on this side here, there is also a layer of clay, which has been moved into the fault. And this is the part which is sealing. It is a very thin layer of clay that is the barrier for the fluid flow. Okay. So I've explained to you faults which can be conduits for fluid flow. I've explained to you or given you examples of faults which are smeared with clay, and they are the barriers for the fluid flow. And I would like to finish this lecture with an example of one of our research projects of a special kind of faults which you find in basalts. Of course, basalts are quite important rocks, but mostly they are on the ocean floor, so you don't see the basalts. But faults in basalts are very common all over the mid-oceanic ridges. On Iceland, where these mid-oceanic ridges exposed, you see a lot of these faults, and some of the oceanic islands like Hawaii also have basalts with faults. So we went and studied some faults on the island of Hawaii as one of the Diplomarbeiten in my institute. So this is, Hawaii is in fact a very active and earthquake-prone island. You get signs like this, fault zone, watch for cracks in the road. These faults are actually moving, and it might crack up the road from one day to the other. This is a picture, a digital elevation model of the island of Hawaii. Here is Mauna Kea, here is Mauna Loa. And the sides of these islands are collapsing very slowly because the islands are very unstable. And on the digital map, you can see these faults. You can see these sharp breaks in the basalt surfaces. If you go there, of course, what you find is quite regular lava flows. You have all seen the movies of Hawaii where the lava is coming out of the active volcano. But when the lava solidifies, I've now made a detail of the same area here. Then the lava, the solidified lava, forms faults. And this whole side of this island is full of faults. These are all big fault zones. The sides of the island are slumping into the sea. And what we did is we studied these fault zones in the field. And this is how they look like. Okay, so this is maybe 10 meters. And this is the top side of the fault. And then there is this lot of rubble here. And this is the bottom side. And in between the two, we have the fault zone. Here's another example. These faults have big openings in them. Some of them are so big that you can drive a bus into the crack. Okay, so here you have huge openings in this faulted basalt, and these cracks can be hundreds of meters deep. If you drop a stone, you don't hear that it actually touches the bottom. And one of my students, Mark Holland, has made a detailed study of these faults. And this is the picture that he has drawn. Okay, so here at depth, there is a normal fault. And there are, on the top of the fault zone, there are enormous fractures and blocks which are rotated. Until now, we haven't really known a lot about fault zones in basalt. And it is also very difficult to study these faults. because of course it's very dangerous to climb into these cracks in the earth. So nobody has taken the trouble to actually go down and have a look. And what we have done is we have made a model in the laboratory. So this is Hein, who is now one of our students, and he made a model which is down here by sprinkling powdered gypsum in layers. And then he made a graben model. So we have taken this wooden block and pulled it down. And this picture is the end of one of these experiments. And what you can see is that it reproduces at a small scale many of the features which we see in these normal faults in nature. So I will now go to the experiment again. I think I have to click on it. Yeah. Okay. So here is our model of a fault in basalt, like you see on the mid-oceanic ridges or on the island of Hawaii. The bottom is a broken or faulted basement with a normal fault in it, with a graben, and on top is a sequence of basalts. Okay? And then what we do is we move this central block down. We start to move the graben, of course, because of that the model extends. You move down the graben, the two halves move apart, and you start generating these cracks. Until now you don't see very much yet. But after a few centimeters of movement, what you form is you form these enormous cracks going down from the surface. And this model is a small version of the real world. So a crack which is 3 centimeters can be 300 meters in nature. You can see some very sharp displacement here, real faults. And here you start seeing these enormous blocks. Okay, and if you have concentrated on this part of the experiment, you can see that this block is rotating and it kind of covers the fault zone. This fracture here has opened up. There are big reliefs